In this video, I'm going to discuss how to tackle vector proofs. So things to know for proofs. I'm going to go over a few things before I do two examples. So first of all, point-to-point vector addition. So what do I mean by point-to-point? So if we have point A, B, and they're connected together, we can call it vector AB. So this is where you have vectors that are not called by a single letter like U and V. So you actually have two vertices that are used to signify the vector direction from point A to point B or from B to C. Okay, so let's say you're having a proof and you had, these two things side by side added. What can you do with that? Well, if you look at the diagram, vector addition will tell you that if you started at point A, you went to B, then to C, your start and ending is the key thing that you want to remember with vectors. So you start at A, end with C, so technically this can be collapsed together, or you can think of it as a shortcut. Instead of going from A to B, then to C, you can go straight from A to C. You can collapse them together as long as both of them are positive and B on the inside matches. So in the end, this is equivalent to just saying AC. So you don't have to actually see this picture to be able to do this collapse, okay? Now, vice versa, this could be done as well. Actually, in vector proofs, sometimes you start with something simple. You actually want to rewrite it in a different way. So if you had AC, you could always rewrite it as the long way that you went from A to B and then to C after that, because maybe on the other side of your equation that you're trying to prove, there's maybe this vertex B being used. Okay, so in this situation, you could say that this is equal to AB plus BC, or in other words, you're uncollapsing this to another version, taking the longer way around. So sometimes this is important to use within proofs. Another important thing to note is that if you have 2 points AB, and this red vector BA is pointing from B to A, and vector AB would be pointing the other direction, they would be made equal to each other as long as you put a negative in front and swap the order of the letters. Why is this one useful? So if you take a look at this expression here, you cannot put these two together because they're not addition in between. So what you could do is rewrite this last one as positive CA. So swap the order A and C and change the minus to a plus. This then allows you to collapse these two together to say this is just BA. Adding with AB before that, you can collapse that even further and say this is point A back to itself, which means you haven't moved or you have vector 0 in the end. So this is sometimes useful to be able to swap the order of the letters and change a positive to a negative or vice versa. What else can we do? Well, if you're told something about midpoints, A is midpoint of BC. So this tells you then that A is right in the middle, and size AB to AC, they're identical, indicated by these tick marks. So obviously BA would equal to AC, so make sure you follow the order B to A, meaning it's pointing down and to the right, just like AC down and to the right. But what can you say about the whole thing? You cannot say both of these are also equal to BC as well, because BC is much longer, twice as long. So what you could say is that 1/2 BC is equal to the other two. So there's lots of things you could say about these, but as long as you're given a midpoint, you can create some relationships from that. So these could be useful. And midpoint cuts it right in half. You don't have to have it cut right in half. Here's another example. Let's say BC is cut by A in the ratio of 5 to 7. So from AB ratio to AC is the same thing as 5 to 7. This is a reduced ratio. So from AB, we place 5. A to C, we place little 7 to indicate proportionality here. So one of the relationships you could state is the following. 5/12 of BC is equal to BA. You might say, well, how would you even know that this is the relationship. Here's my explanation. So what you could do is set up a proportionality like you've done in similar triangles. We can have on the numerator things to do with a part, and on the bottom to do with the whole thing, like the biggest possible, okay? So if we have BA, so BA is not the full thing, so you can think of it as like one part, and BC is the whole thing, right? So then BA, we know the size is 5, but the whole thing is 5 plus 7, which is 12. So how did I get the red part? Well, you could see that I basically took this BC and half cross multiplied to the other side to get this relationship. This is not the only relationship you can come up with. Let's do just one more, but there's multiple ones. If you wanted to do not the whole thing, but just smaller portion versus the larger portion, for example, BA, so that's the smaller portion, and then AC is the larger one, but it's not the whole thing. That relationship is 5 to 7. So again, if you half cross multiply, you can get this relationship, that BA, so still pointing down and to the right, just like AC I'm using here, down and to the right. So you have to make sure the order of the letters matches. And we have 5 7s as a coefficient in front. Next, if you have parallel vectors, sometimes instead of using the word parallel, question might say collinear. That means the same thing. They fall on the same line. So this is just an example before I put the final result over here. So suppose somewhere in your proof you came up with a relationship for vector AB in terms of x and y vectors. And then vector CD, you found out the relationship is exactly what AB was, but half of it. This would imply that AB is parallel to CD. This is the main relationship, that if you can stretch one by a scalar multiple or compress one by a scalar multiple to get the other, as long as k is any non-zero number, then they're going to be parallel vectors or collinear vectors. And a couple of clarifications. Some videos and worksheets will use the following, and I just want to clarify or make adjustments that I think would have been better. So they would use bold font on a vector. So you can notice how it's kind of darker here, AB here, instead of putting A with a vector symbol over top. So I would prefer that you would just use vector symbols. And second thing that sometimes they do is they would place an arrow in the middle of the vector, so AB, and then this arrow is kind of in the middle to show the direction of the vector, instead of putting the arrow at the end to indicate the length of it. So I would prefer that you would fix that up so that the arrows go right to the end of this vector OA is all the way. Okay, time for the two examples. So this one, it says, if side BC of triangle ABC is trisected, so cut in 3 parts, 3 equal parts, by points PQ, show that this relationship is true. So first of all, the word trisected. Let's put PQ and indicate by tick marks these 3 slices are identical size. Then I'm going to do left side, right side chart just to keep one side the same and work with one side only. So I notice how on this right side we have AP and AQ. So what I'm going to do is leave that side alone and change this so that it uses AP and AQ somehow. So first, we can say AB, if I were to uncollapse it using point P, you would say instead of going from A to B straight, we'll go at the long route. We'll go from A to B, or sorry, A to P, then P to B. That's the same thing as going from A to B straight. So that's this part. AC, you could do the same thing, because on the other side there's also a Q. So let's use Q as a long route. So instead of going straight from A to C, you go through Q. So A to Q, and then Q to C is the same thing. Now we have AP and AQ like we want on the other side, but this part here and this part here doesn't match. So let's think, what else can we do? I have color coded now. PB is going to be this blue color. So that's this vector here. And QC pointing the other way, black. So this gives us a relationship that PB, so pointing upwards, and CQ then pointing upwards, we're going to be identical because they're going in the same direction, they're collinear, and they have the same size indicated by this tick mark. So this PB, I can rewrite it as CQ. So now putting all together, we notice that there's some like terms that we could possibly maybe change the order a little bit. No, I'm going to change the order later. I'm going to collapse these two things together. So notice how there's both of them are addition. So addition in front here, addition in front here, and Q is the letter that is in the middle. So we can collapse this to a shortcut to go straight to AC. Then this AC and these two just copy down. I'm going to change the order now. So then this AP plus AC plus CQ. Notice how you could again do this collapse on these two vectors. You get AQ, and then AP plus AQ is actually what we were trying to solve for or prove. So left side does equal to right side, and this one is done. I do want to say that this particular proof is not unique. You could have totally went in a different direction. As long as every step that you make is valid and you justify it somehow, then you're good. One more example. If T divides AB in a ratio of 2:(-1), prove the following relationship. So it's a little bit weird to have a negative in the ratio, but I'll show you how to think through it. So first of all, we're going to try a picture that's actually incorrect, but just to kind of talk through it. So whenever you're given a ratio, you could just put in T in the middle, even though it might not be in the middle, and just put in the size 2 from A to T and -1 from T to B, because T divides AB in this ratio. However, because the length can't be negative, here's my better picture. T is actually on the other side, so this negative indicates that T is supposed to go on the other side of B. So from A to T all the way, that's size 2, and then back 1 is where the B is located. Okay, so it's a little weird question, but if you see this type of trick question, this is what it means. Then this O here, I already mentioned that it stands for origin. So whatever you're trying to maybe create a proof using origin and you haven't drawn it, you could just place it wherever you wish. So I placed it over here. Okay, so here's my setup of left side and right side chart. So on this right side, I see that there is a B, but here I don't see it. So maybe we can go from OT and collapse it, or go the long route from, instead of O to T, we go O to B, then B to T. Take the long route. Now at least we have OB here and OB here. There's supposed to be 2 of them. So let's think, what else? Notice how on this side there is no T at all. So this vector doesn't have T, this vector does. So let's maybe work with this one. So if you look at the diagram here, BT is actually going to be equivalent to AB. How come? So looking at this picture, we have BT is in the same line as AB, and we know this is going to be size 1, based on the relationship we wrote down above here, size 2 versus size 1 here. So this is cut it exactly in the middle. B is midpoint of AT. So BT pointing upwards and to the right, and AB also pointing upwards and to the right, they're going to be equivalent. So instead of BT, we can rewrite it without using T at all, just saying AB. Here it is. What's next? So I notice again here, we have on this side, everything to do with origin. So all vectors use the origin, but this AB doesn't yet. So once more, we can uncollapse or go the long route from A to origin, and then from origin to point B. So here's a picture of that. So instead of going from A to B, we go from A to origin, then origin to B. Okay, so we have that. Then rewriting it, and we have some like terms. OB can place together, and collect them to make 2 of them, just like what we want. And this AO, if you change the order, you can change positive to a negative, and that gives you the proof that we wanted.